Good morning, everyone. My name is Prof Ong, and I'm a professor at UC San Diego, and my lab is called the Materials Virtual Lab. Today, my talk for the GTC 2021 conference is titled Discovering New Materials in a Fraction of the Time with Graph Networks. So, as many of you may well know, materials actually underpin a lot of the technologies that we use today. From the lithium-ion battery in your cell phone and laptops, to things like post-it notes, to solar cells, all these are technologies that are underpinned by new materials discovery. Traditionally, new materials are discovered primarily through the lab, and there's this famous quote by Thomas Edison that many of you should have heard of. I have not failed, I have just found 10,000 ways that won't work. Now, the problem with this traditional way of materials discovery is that it takes on average about 20 years and billions of dollars of development to bring a material from the lab to actual commercialization. Now, Thomas Edison has a very famous rival, and that is, of course, Nikola Tesla. And Nikola Tesla was quite disparaging of Thomas Edison's approach. He basically said that if Edison had to find a needle in a haystack, he would basically look at every single piece of hay, but with just a little theory and calculation, we could have saved about 90% of his labor. Now, even Tesla could not have foreseen the computing power that we would have at our disposal today. And in fact, it's not just a little theory and calculation, but rather a little theory and a lot of calculation that can allow us to significantly accelerate the pace of new material discovery. So the holy grail in material science is basically to be able to predict the properties of materials directly in a computer without actually having to go to a lab to synthesize the material. Now, in the past few decades, this has become a reality. So the type of calculations that my group specializes in are what are known as first principle calculations. In other words, calculations that utilizes the fundamental laws of physics, like the Schrödinger equation. The way that this works is you take a crystal or a molecule, and you essentially take the elements that are in the material together with the position of the atoms. You plug that information into a computer, and you then try to solve the Schrödinger equation for that system of atoms. And what pops out are basically material properties from your calculation. Now, today we can compute a lot of material properties using this approach. We can calculate things like the energies, the band gaps, the mechanical properties such as the bulk modulus and shear modulus, and optical properties such as the dielectric constants. Now, once we are able to predict those properties with a good amount of accuracy, we can then use that to solve real-world problems like designing better batteries or designing better solar cells. However, even this approach has its limitations. So the problem with this kind of first principle calculations is that they scale very poorly with the number of atoms in your material. So most first principle calculations scale at least n to the power of 3 or even worse with respect to the total number of atoms. This means that if you have 100 atoms versus 1 atom, you are essentially looking at 1,000,000 times the computational cost. With the reason why we are interested in recent years, machine learning has become such a big topic in material science is that we want to basically shortcut this process of first principle calculations. So we already have a lot of data from first principle calculations. So can we use that data to basically develop machine learning models that can learn the relationship between from the arrangement of atoms to material properties? Now, in the process, what we hope to do is, of course, to be able to use such machine learning models to predict properties much more efficiently than would otherwise be possible, which would then allow us to explore much larger spaces of structures and chemistries for new materials. So combinatorial generalization is in general how humans learn, right? So if you think about the 26 letters in the alphabet, the same 26 letters can be used to, say, compose a sonnet, which is what William Shakespeare does, or we can also write dry scientific papers, which is what my group does. Now, in the context of materials, developing new materials, we do combinatorial generalization by essentially thinking about, given a certain crystal structure prototype, what sort of elements can we swap for each other to develop potentially new materials, right? However, combinatorial generalization also takes place in the context of a hierarchy of structured knowledge. And we have built this hierarchy of knowledge in the past few centuries, right? So we have things like the periodic table, which tells you how certain elements have similar properties. We have the laws of thermodynamics, which tells you which properties are related to one another. Some properties are actually extensive properties, which means that they actually scale with the total number of atoms, or which properties are actually intensive properties. There's also the concept of locality of interactions, which simply means that atoms that are close together tend to have stronger interactions than atoms that are very far away. The other kind of knowledge is things like symmetry constraints, right? So if you take a set of atoms and you move them in a certain direction, or you rotate those atoms, in general, the property of that material shouldn't change. So the ideal situation is that we can incorporate all such structured knowledge within the representation of a material itself. And in doing so, we actually then impose all these constraints, and that makes for a better machine learning model that have these properties by design. So the type of machine learning model that my group has worked extensively on is known as graph networks, which was actually mine back in 2018-2019. So in graph networks, basically we represent materials as mathematical graphs with information flow. So this is actually a very natural representation for materials. So we can think of the nodes in the graph as basically the atoms in the material, and the edges in the graph as the bonds between the atoms, right? And in a graph network, basically you then allow information to flow between the elements of the graph network. So typically it's a three-step process. You basically have a bond update in which you take the atoms that are forming a bond together with the global state vector, and you update the information in the vector of the bond itself. And then this is followed by an atom update in which you take all the bonds that are emanating from an atom, and then you update the atomic information. And finally, you have a global state update in which you update the global state vector with information that pertains to the overall state of the material. Now, the nice thing about graph networks is that this is a very modular approach to developing machine learning models, right? So we have developed what is known as materials graph networks, basically which in essence an adaptation of graph networks for material science. So we can think of each of those three-step update processes as essentially what we call a magnet block. And you can then stack multiple magnet blocks to create machine learning models of arbitrary complexity, right? So the more blocks you have, the greater the range of interactions between atoms that are far away, and certain properties require fewer magnet blocks than other properties. So we have actually made this entire implementation open source, and you can actually find the source code at GitHub at this link right here. Now, in order to train our graph network models, we actually depend heavily on GPUs to do the training of the machine learning model. So typically we work with on the order of at least 1,000 to hundreds of thousands of crystal structures with anywhere between 1 atom to 100 atoms in the unit cell. So this simply means that we actually have a lot of data, and we have very, very large graphs. And the GPU acceleration allows us to basically process these graphs and to train the machine learning model at least about a 10x speed increase compared to just using traditional CPUs, right? So this is what you see in the graph on the right over here. Now, how well does do material graph network works? So we have this big database of material properties, which is called the Materials Project, and we have developed MEGNet models for a variety of properties that have already been pre-computed in the Materials Project. So there are a few basic properties. So things like, for example, the formation energy of a crystal, which is of interest because you want to know how stable a material is likely to be and whether you can actually synthesize it. There are things like the band gap, which is electronic structure property that is of major interest in developing things like solar cells and optoelectronic materials. There's also things like the bulk and shear modulus, which are of interest in structural applications, right? So I'm going to just quickly talk about the formation energy. So you will see that we have, using MEGNet models, we can achieve mean absolute error of about 28 MeV per atom in predicting the formation energies of about 60,000 crystal structures in the Materials Project. Now, this is a cross-validated mean absolute error, so this is not just the training error, right? Now, is 28 MeV per atom enough? So the way that we check this is that if we look at this previous work, which studies all the known experimental materials that have actually been synthesized before, and we look at the distribution of the energy above the ground state, we find that about 80% of the materials fall within about 70 MeV per atom in energy from the ground state, right? So given that our error is about 28 MeV per atom, this is generally good enough for making decisions or predictions about whether a material is likely to be stable or not, right? Now, however, you will also notice a fundamental problem with materials data, which is that there's a lot of heterogeneity. So things like, for example, the formation energy are relatively easy to compute using first principle calculations, which is why we have a lot of data for it. But things like, for example, accurate band gaps tend to be fewer, and things like the mechanical properties tend to be even fewer, right? So these are, in general, about an order of magnitude fewer data points than things like the formation energy. So what we have found is that transfer learning of the elemental embeddings actually significantly improves our convergence and accuracy. So in our MEGNet models, the input to our atomic descriptor is basically just the atomic number of the atom, right? But this is done through a length 16 embedding vector. Now, what we have found is that by taking that length 16 embedding vector and by doing transfer learning of that embedding to another model, so say we take the formation energy model, which has a lot of data, and transfer it to a band gap model, and then we retrain the model using this transferred embedding, we can actually significantly improve the convergence speed as well as decrease the mean absolute error in our predictions. And this works even better for properties with fewer data points. Now, the reason why this works is that if we take the embeddings and we plot the correlations between embeddings for all the elements and from our trained materials graph network models, we found that essentially the correlations between embeddings actually reproduces the periodic table of the elements. So in other words, elements that tend to be chemically very similar, so things like, for example, lithium and sodium, who are both in the first column of the periodic table, tend to have very high correlation, while elements that are very chemically dissimilar have very low correlations in their embeddings. And you can also see that in the TS&E projection, where chemically similar elements, which are colored similarly in this graph, tend to be clustered together in the TS&E plot. Now, just recently, we have actually further extended our materials graph network models to solve another fundamental problem in applying machine learning to material science. And the fundamental problem with materials data is that high value data, such as experimental data or accurate calculations, tend to be very, very expensive to acquire and therefore are scarce. So if you look at this pie chart over here, you will see that we have actually a reasonable amount of data on band gaps of materials that are computed using this method known as the PBE functional. Now, this functional is well known to be quite inaccurate, but hence it is also the least valuable. However, it is also the cheapest way in which you can calculate the band gap of a material. Conversely, there are more accurate methods that you can use to calculate the band gap. So things like, for example, what is known as the HSE functional. There's also other methods, for example, the GLB and scan functionals. And of course, you can also measure the band gap of a material directly in experiments. Now, what you notice immediately is that all those data sets, the high value data, which are the accurate calculations and the experimental data, are about an order of magnitude or more smaller than your least accurate data, right? And this band gap is actually a very critical property of a material that is of interest in many different applications. So things like solar cells, you essentially need to know the band gap of a material to design a good solar cell. So the way that we try to address this data problem is through what is known as multi-fidelity graph networks. Now, if you recall, in our graph network representation of a material, there is this global state in which we actually use to incorporate properties of the material as a whole, which do not depend on the atoms or the bonds. So here we actually, in multi-fidelity graph networks, we take the fidelity of the data, so things like whether it comes from our least accurate PBE calculation or is it an experimental data, and then we embed it in this global state, right? And then we perform the remainder of the materials graph network remains unchanged. And what we found was that by using multi-fidelity graph network models and incorporating all the data together in a single model, we can significantly improve the model performance, right? So this is the performance, the mean absolute error in the band gap for each of the data, if we develop materials graph network models for each of the data sets individually, right? And you can see, of course, the PBE has a very low mean absolute error, but the smaller data sets, like the HSE and the experimental band gaps, have a much larger mean absolute error. By incorporating, by using multi-fidelity data with the multi-fidelity graph network, we can actually achieve about a 40 to 50% improvement on the high value HSE and experimental band gap predictions. Now, in essence, this means that we can actually get the best of both worlds. We can utilize the very large data set that we have on PBE band gaps, which are not very accurate, but yet we can still significantly improve the performance on very high value data, which have much smaller data sets. Now, why do multi-fidelity graph networks work? So we can actually take the latent structural features with and without adding the inaccurate PBE data, and we plot the TSNE plot of the latent structural features, and we see that essentially without the large data, we actually have not a very good separation of latent structural features between very high band gap and low band gap materials, while if we actually incorporate those incorporate the large PBE data, we get a much better separation of latent structural features. In other words, the large PBE data, even though it is inaccurate, it actually significantly improves the latent structural representations, which then leads to better performance on the smaller data set. So we have applied this approach to essentially doing DFT discovery of new materials. In other words, discovery of new materials without using first principle calculations, which are very expensive. Now, basically what we do is that we use Bayesian optimization together with our materials graph networks to do relaxation of crystals, and we then incorporate that into a workflow in which we screen about 400,000 new crystal structures to discover potentially new materials that are hard, very hard, and ultra incompressible. Now, the proof is in the fact that we have actually managed to discover two completely new ultra-hard incompressible materials in the lab. So our collaborator has actually managed to synthesize them and confirm that they actually have the properties that we actually predicted them to have. So this is something that is groundbreaking, right? Because this is, I would say, probably the first time that we have shown people have shown that you can actually use a machine learning model to predict a material, and we have actually realized that material in the lab. And this is not screening 400,000 materials is not something that you can do using traditional first principle calculations. So to conclude, basically we have a hierarchy of knowledge as well as a hierarchy of data, right? So for the hierarchy of knowledge, so things like known physics and chemistry, we want to encode them into the representations where possible. For things like intuitive interactions, such as the range of interactions, we can use flexible representations such as the materials graph network. And for unknown relationships, of course, we have to rely on our machine learning model to learn those relationships. Now, I have also shown that there's a hierarchy of data in the in material science. So things like cheap and less accurate calculations, we can use them to learn latent representations that are better for predicting properties. We can also perform more expensive computations to enhance the accuracy, and for expensive experimental data, which are very, very difficult to acquire, we can then use our improved models to predict them. So to conclude, and finally, I would like to acknowledge the efforts of my assistant project scientist, Dr. Chi Chen, who was responsible for most of the work that you see today. And I also would like to acknowledge funding from the Samsung GRO program, as well as the DOE through the materials project for all the work that was done. And if you are interested in finding out more details, you can check out these two publications that you see in this green box over here. And we actually also have a YouTube channel with some of our talks on the subject. And thank you.